So in this problem, we're going to apply the double integration method to calculate for a cantilever beam with a linearly distributed load starting from 0 to 3 kip per foot, 9 foot long, the maximum slope or maximum rotation or slope, and the maximum deflection of this cantilever. And usually, just by properties of cantilevers, when you have a loading like this all in one direction, um, the maximum deflection and rotation are usually at the tip of a cantilever. Okay, so that's just something to know because this is fixed. The slope here is 0 and it increases gradually as you go to the end of the beam. So the first thing we're got to do here is, and we're asked to use this coordinate system using x defined here from 0. Okay, and so the first thing that we need to do is, as always, is calculate reactions. Calculate reactions. Okay, or draw a schematic and calculate the reactions. So in this schematic here, really we have AY for the fixed end, a concentrated moment MA here, and AX here. Okay, and really you can draw those in any direction as long as you understand that the negative sign that you get from a global equilibrium equation means that it's going in the opposite sense. Okay, but here, so by doing that, if I sum forces in the y equal to 0, or the vertical, right here, I have AY minus the resultant of this, the triangle, which is, I'll put the purple arrow here, and that's going to be 1/2 the base, which is 9 feet, times, I'm talking about the area of this triangle right here, times 3 kip per foot, which is, what was that number again? 13.5 kips equal to 0. Okay, and that tells me that AY is equal to 13.5 kips, and my positive result indicates that my sense or my direction is correct. And I then, to calculate the moment at A, at the fixed support, the moment equal to 0. I'm going to sum moments about a point. I'll sum moments about this point right here, okay, about the dot, this dot, okay, equal to 0. And I would get here MA, the reaction, minus the resultant times the distance from here to the resultant. And that distance is the centroid of this triangle, which is 2/3 from the 0 side. So this is, the resultant is 13.5 kips times 2/3 times 9 feet equal to 0. And then I get that MA is, what is that? 3, 6, 81 kip feet. And the positive indicates that my sense of this MA is also correct. That means, and it also means that I know which side compression and tension is going on too, right? At least at the support. I know that tension is at the top, compression is at the bottom, and then really no other boundary conditions are going to affect that, so I know that's going to be true for the entire length of the beam. Anyway, so if you get this wrong, you're going to, you're going to get the whole problem wrong. So it's really important that you get these reactions right. Okay, so now we have that, and so in order to use the double integration method, we want to come up with a moment function as a function of x here. So we're going to make a cut here, right here. So let's do the moment function. So 2 is the moment function. And this moment function, I'm going to draw a schematic of it again. Here, I'm not going to draw the whole beam out this time. I'm just going to draw a little stick right here. I have at the support here, I have 13.5 kips and a moment right here of 81 kip feet. Okay. Internally, for my moment function, I'm going to draw a moment here, which I know is going to be a function of x, which is a cut over here at x. I also have a shear here, but I don't need that shear function. And I also have the distributed load that's also cut right here. whose value I don't really know right here what that is because it's varying linearly from 0 to 3 kip per foot as a function of x. So now let me solve for m here using all these variables, and I'm just going to simply I'll call this point here O, and I'll sum for moments about O equal to 0. So here positive is this way, and so I'll have m, this what I'm solving for, this m. Let's see. Oh, let me calculate the resultant of this. So let me use purple here. This purple. This resultant right here is 1/2 w times x. Yeah, and it has a distance from the cut of x over 3. Yeah. Okay. And here m is equal, so now I have m plus 1/2 w times x. Here's that force. This is a force. That's a force. Times the arm times x over 3 minus 13.5 kips times x plus 81 kip feet equal to 0. And my moment function now is, let's see, minus 1/2 w x squared over 3 plus 13.5 kips times x minus 81 kip times feet. Okay, so that looks good so far, except now I need to know what w is. And w, if I go back up here, w is associated with that point right there. W. And so I can look at, by similar triangles, I can figure out what W is. So here, by similar triangles, I would say W over X is equal to 3 kip per foot over 9 feet. And that means W is 3 kip per foot over 9 feet times X, which means W, let me write that one more time. How many times I have to write it? Kip per foot squared, 3/9 or 1/3 kip per foot squared times x. And so now when I put that into here, my moment function finally becomes minus 1/2 times 1/3 kip per foot squared times x squared over 3, okay, which plus, this term minus this term, okay, which becomes 3 times 3 is 9, so minus x cubed over 18 plus 13 point, oh, let me keep some units here too, kip per foot squared plus 13.5 kips times x minus 81 kip feet. And this is my moment function right there. I think that's the hardest part about this problem, really, is the moment function. Normally, it would be finding the boundary conditions and continuity conditions in a double integration method. But for this particular problem, it's just really the moment function. And so here, now what we need to do is apply double integration. So double integrate. So we have this stinking polynomial, right? So we have this double integration method, double int right here. So now if I integrate this one time or take the antiderivative, I would get EI times dv dx, which is the same as EI times theta, or the slope is minus x to the 4th over 18 times 4, which is 72. Okay. Kip per foot squared. Yeah, that works. Yeah, that works. That works. Plus 13.5 divided by 2, which is 6.75. Kip times x squared minus 81 kip feet times x. And then, oh, plus a constant, I'll call that C1. Okay. Then I want to do EI times V, the displacement function, or the equation of the elastic curve, minus x to the fifth over 72 times 5 is 360 kip over feet squared. Let me know if any of my algebra is wrong, please, or my math. 6.75 kips divided by 3x cubed minus 81 divided by 2 kip feet x squared plus C1 times x plus C2. That looks okay. And now I want to find these constants. So any questions so far? Nothing? Yeah. All right, good. So here 4 is to calc constants, which means we need boundary conditions, and the boundary conditions for cantilever are very easy. And what are the boundary conditions? So v equals 0 at x equals 0, good, and theta equals 0 at x equals 0. And that tells me if I plug in x equals 0 to this first equation, if I plug in x equals 0, I get C1 equals 0. Hey. And then if I plug in x equals 0 to this one, that was easy. C2 equals 0. Yeah? Awesome, right? And then to find the maximums, right, I'm going to plug in numbers. I would plug in numbers for EI that were given. And so to find V max and theta max, just substitute x equals 9 feet into the equations. And just make sure you don't mess up your units. And that's it. Okay.